This lecture covers chapters 10 and 11 in your textbook. And we begin with talking about model averaging and Bayesian learning. So instead of choosing just a single model, Bayesian learning considers multiple possible models and weighs them by how likely they are. And this helps avoid overconfidence in one explanation. In a cyber context, this is like considering multiple possible causes for an alert rather than assuming there's only one correct answer. And here we update our beliefs using evidence. So the prior represents what we believed before, and the likelihood tells us how well the data fits a model. Combining these gives us the posterior, which is our updated belief. And this is the core of how analysts refine their understanding during an investigation. So now to tie this into cybersecurity, in practice, the evidence we rely on is incomplete and sometimes unreliable. Alerts can be noisy, logs may be missing, visibility is limited. So even in well-instrumented systems, uncertainty never goes away. So instead of confirming facts, we are constantly updating our belief about what is happening. And this example here shows how we estimate probabilities from observed data. If we only rely on raw frequency, we can end up with misleading results, especially with small samples. And techniques like smoothing help us avoid extreme conclusions when we don't have enough data. And this example here is an example of overfitting. And you can read through that and see the scenario on the slide. I'm just going to give you an overview again of overfitting. So overfitting occurs when a model fits the training data too closely, but then fails on new data. And in this example, items with very few ratings appear perfect, but that doesn't mean that they are actually better. The same issue appears in detection systems trained on only a limited amount of incident data. Overfitting to the small amount of data can occur. So in cybersecurity, overfitting shows up when detections work perfectly on known attacks, but fail when attackers make small changes. And in that case, the system has learned patterns that are too specific to the past. So effective detection needs to generalize to new and evolving threats. And then let's talk about probabilities from experts. When data is limited, we can incorporate expert knowledge. So instead of relying only on observed data, we can treat expert estimates as additional evidence. And so this allows us to combine real-world observations with informed judgment. And in security, priors come from experience, from known attack patterns, and from past incidents. So analysts bring this context into every decision, and new alerts are interpreted through what is already known. They're not evaluated in isolation. And then let's talk about clustering and unsupervised learning. Unsupervised learning looks for structure in data without unsupervised learning looks for structure in data without predefined labels. So instead of predicting known outcomes, it groups similar cases together. And this is useful when we don't know in advance what patterns we are trying to detect. And then applying this to security in real environments, clustering helps define what normal behavior looks like. Once normal patterns are established, then unusual behavior becomes easier to spot. So this is often how previously unknown threats are first identified. Now let's talk about the k-means algorithm. So k-means is a simple clustering method that groups data based on similarity. It assigns each data point to the nearest cluster and then updates the cluster centers. This process repeats until the groups stabilize. And the goal is to minimize differences within each cluster. So once clustering is applied, most activity will fall into expected groups. And the interesting cases are the ones that don't fit well into any cluster. And these outliers often represent unusual behavior and are typically where investigations begin when we're talking about security investigations. It's the outliers that would trigger the investigation, the ones that don't fit well into any cluster. And k-means has several important limitations. It can get stuck in local optima, meaning it doesn't always find the best solution. It is also sensitive to how many clusters we choose and to the scale of the data. And these factors affect how reliable the results are. And so then let's talk about why clustering results needs caution. Because of these limitations that I mentioned on the previous slide, clustering results must be interpreted carefully. Normal and malicious behavior can overlap, and attackers may intentionally mimic normal patterns. Clustering helps guide analysis, but it does not provide definitive answers. And the EM algorithm, and that stands for the expectation maximization algorithm. It is used when some variables are hidden. It alternates between estimating missing information and updating the model. Over time, it converges to a stable solution that best explains the observed data. And so in cybersecurity, of course, we never directly observe whether a system is compromised. Instead, we observe logs, alerts, and behavior. And then from that evidence, we infer the hidden state of the system, such as whether it is normal or compromised. And so that algorithm we just talked about, the EM algorithm, it models situations such as in security where key variables are hidden. That's how that applies. And now let's talk about causality. Causality focuses on what actually produces an effect. A variable is considered a cause if changing it would change the outcome. This is different from correlation, where two things may occur together without one causing the other. So here we're talking about causality, where one does cause the other. So to continue, causal models represent relationships between variables and how they influence one another. So these models allow us to predict what will happen when we intervene in a system. And not all probabilistic models are causal, even if they look similar. And then here's a sprinkler example. So this example highlights the difference between observing and intervening. Seeing that the sprinkler is on is different from turning it on yourself. These two situations lead to different conclusions, which is central to causal reasoning. And then here's an example. Drowning and eating ice cream. This example shows that correlation does not imply causation. Ice cream sales and drowning incidents both increase in warm weather, but one does not cause the other. A third factor, such as temperature, higher temperatures in the warm months, explain both. And then the model here just elaborates on that. And another thing you'll read about in the chapter this week is do notation. And as you can see it here on the slide, and do notation allows us to represent interventions explicitly. Instead of just observing that something happened, we ask, what happens if we actively set a variable to a value? This distinction is critical because observing and intervening can lead to very different conclusions. And then applying it to cybersecurity. In security operations, this difference shows up clearly. Observing an alert means we are gathering information. Intervening, such as disabling an account or isolating a system, changes future outcomes. So these are fundamentally different actions and must be treated differently in analysis. And then let's talk about missing data. So missing data is not always random. Sometimes the reason data is missing is directly related to what we are trying to measure. For example, if certain events are more likely to go unlogged, ignoring that can bias our conclusions. So in general, you need to model why data is missing. And then we'll talk about recoverability. So recoverability asks whether we can still estimate the true distribution despite missing data. If data is missing in a structured or biased way, then our estimates may be unreliable. In those cases, simply analyzing the available data can lead to incorrect conclusions. And Simpson's paradox shows that trends can reverse when data is aggregated. What appears to be true overall may not hold within subgroups. So this highlights the importance of analyzing data at the appropriate level of detail. And then applying this to cybersecurity. In security, This can happen when overall metrics improve while critical systems get worse. If we only look at aggregated data, we may think things are improving when they are not. So breaking the data down by context is essential and looking at it at the right level. And now inferring causality means determining whether one variable actually influences another. And this is more difficult than identifying correlation because multiple factors may be involved and not all relationships are causal. And in security incidents, confounders are hidden variables that influence both the cause and the effect. And in security incidents, multiple factors often occur at the same time, making it difficult to isolate what actually caused the outcome. Because there could be confounding variables other than the one that actually did cause the outcome. So counterfactual reasoning asks what would have happened under different conditions. It combines what we observed with hypothetical changes to evaluate alternative outcomes. So that's what counterfactual reasoning does. It's asking, what if something else were true? And so here's an example of a firing squad. So this example illustrates how multiple contributing factors can complicate causal reasoning. Even if multiple actions contribute to an outcome, determining responsibility or necessity requires careful analysis of counterfactual scenarios. And then finally, another example, or applying it rather to cybersecurity and talking about counterfactual analysis in cybersecurity incidents. After an incident, analysts ask what could have changed the outcome. So questions like whether earlier detection or stronger controls would have helped are examples of counterfactual reasoning. And this process helps improve future defenses. So that concludes chapters 10 and 11.